Hello everybody, this video is about hyperparameter tuning using GridSearchCV with Ridge Regression as an example in Jupyter Notebook. So let's go to Jupyter and start working. So let's load the data. So plugging the data set. We need to import pandas library. So import pandas SPD. Then we read the data, load it. So let's call it my data. We call ed.read underscore comma separated value. This is the directory where the data is found here on my computer. And the dataset name is flood.csv. Okay. So sorry. There was typo here. So pandas as PD. Sorry about that. So let's set the seeds to 7. This is to make our code reproducible, and let's see what is in my data just by typing my data. This is what you have: time, area / the flooded area. This is our dependent variable target. And you have relative humidity, evapotranspiration, precipitation, air temperature, soil moisture, ground heat flux. These are the independent variables or predictors for features. So let's see my data that describe to have an idea about the descriptive statistics there. Okay. So let's prepare the output and input data. Preparing. Let's have our Y target. The output variable. So Y, as I said, is the flooded area. So we are going to take area out of my data. So let's have its shape. And the shape. dimensional array 3994. Let's print its few first rows. Say 5. Okay. Now let's have our features. Features. Input variables. X. So X, we are going to drop from my data target variable and the time. Okay, I hope the syntax is okay. Okay. And axis equal to 1. Let's have an idea about the shape of X. We have 3994 observation with 6 variables. Let's add more columns. Let's print let's say the 3 first rows. So this is what we have. Okay. Here you need to run the variance inflation factor and scale your data at this level. The X's, the features, especially for research purposes before continuing, because at this level we are going to split the data set into test training and test data set. And for this we need to import the function train test split. So from scikit-learn.model underscore selection, import train test split. Okay. Now splitting the data itself. We have X train, X test, Y train, Y test equal train test split. We need X, we need Y, we need the size of the test, the testing data set. I take 25%. Here is underscore. random state 30 and shuffle equal to true. Okay, and we run it. Now let's have an idea about the shapes of our data sets or sub data sets here. Print x train dot shape, x test dot shape, y train dot shape, y test dot shape. Here again underscore instead of dash. Okay, so it's okay now. So these are the shapes of our respective sub data sets, train and test. Okay, so now let's import the necessary libraries and functions we need. For the grid search, so importing necessary functions and the libraries. Okay. So we need our Ridge Regression. So from scikit-learn.linear model, model, we need to import Ridge. Normally we need grid search now. From scikit-learn model selection, model selection, import GridSearchCV. We need k fold and cross-val score. We need the matrix now, so from scikit-learn.matrix we need to import add to score, min absolute error, and the min squared error. These are the three metrics we need. We need to import NumPy as NP, and from NumPy we need absolute. To have the absolute values of the negative values we have. Now we may have some messages, warning messages we need to suppress. So we need to import function to ignore warning messages. So let's import warnings first. Then from warnings we have the filter. Warnings dot filter warnings, and this is code below. And we close. Good. So you have what we need as functions in the libraries to run the GridSearchCV. Then we reach the hyperparameter tuning. Okay, here using Ridge Regression. So let's have our model, which is Ridge. Then we need the parameters. Let's go RG underscore params. Curly brackets. Let's close them at the same time. Then here. So here we need the solver. And the solvers we have SVD. We have PolST. We have LSQR. And SAP. Then we need alphas values. So alpha let's have 1e minus 5, 1e to the power minus 4, 1e to the power minus 3, 1e to the power minus 2, 1e to the power minus 1, 1, 10, and 100. Just examples. And fit intercept, true or false. 3. Let me check the syntax. Okay, now we need the cross validation, the Ridge CV. Equal pre-fold. We have a number of splits. Let's take 5 for the sake of time. Random state. For 1. Shuffle equal to true. Now let's have our grid object now. RG grid. So grid search CV. GridSearchCV. So we have our model, which is RG. Okay, let me put it RG here, RG model, RG model. So put it here also, RG model. So Ridge Regression model. And then we have our RG params. So after our RG model here, RG params, and then our cross validation is going to be RGCV. Then scoring equal to negative mean squared error and end jobs equal to -1. And now we are going to hit our grid objects, rg.grid, dot fit. We fit on x and y, the whole data set. Okay, that is. Let's run, let's see. Okay, fold not defined, so sorry for the typo. Okay, fold here, K, fold. K in capital letter, F in capital letter, as here, Okay, fold instead of F in lower letter. G is not defined. Where is G? It's not defined here. RG model, RG params, RGCV, RG underscore grid, RG underscore grid, sorry, again, RG underscore grid dot fit. rg_grid.fit. Okay, negative mean square here again. Ooh, lot of typo. Next. Good. Let's go ahead. So that's okay now. So it's running. You see here, no error message. Okay, good. So you already have the result. So here, let's print the best parameters and the score. So print the best parameters are rg_grid dot best params underscore. So alpha 1 to the power minus 5 fit intercept equal true, solver equal Cholesky. And let's print the best score is rg_grid dot best underscore score. So this is the best score. Now let's fit on. Let's use these parameters to create the model and fit it on the training data set. Ridge Regression modeling using the best parameters and fitting it on the training data set. So initialization, our model equal Ridge and we have alpha equal to 1 e minus 5 we have fit intercept equal to and we have solver which is Cholesky. Oops. Okay. now let's add fitting. Let's fit it. To the training. So let's call it ridge equal model dot fit on X train on the Y train. So what it fits. So let's evaluate the model on training data set. Model performance. Evaluation. And the data set. For this, we first need to predict on the training data set. So the object is rg predtr equal rg dot predict on X train. Then let's print the R square the training R squared is R2 score we have Y train, so the observe, and then we have RG predtr. Okay, so the training R square is about 66%. So let's have the mean absolute error. The training mean absolute error is mean absolute error of the observed data and its corresponding predicted, which is RG predtr. So the training AE is, let's have the training MSC. MSC is mean squared error Y train on the predtr predicted. Good. This is the metrics on the training data set. So performance evaluation on on the testing data set. We first need to have the prediction on testing data set. So red on TS equal RG dot predict on X test. Then print dart to score the testing R square is to score Y test right TS. And the MAE, the testing MAE is mean absolute error Y test RG red TS. We'll print the testing MSC is mean squared error Y test RG red TS. Okay, we are good with this, so let's go to the cross validation now. Cross validation on the training data set. So let's call it RGCVTR RG_CV on the training data set. So equal cross val score RG X train Y train scoring equal negative. Let me verify syntax here. Negative mean square error and cross validation, the number of full equal to 5. Normally it should take 10. For research purposes 10 is better, but yeah, here I put 5 for the sake of time for the video. So let's run it. this code we need to print the, okay, if we take let's have it, the CVTR, type the object, this is what we have for the 5 folds negative values. We need the absolute of it, so print the absolute min train CV score is absolute np dot min of rg cvtr. Okay, so it's going to give us the mean of these 5 and put it in absolute value. So you have positive because we put here negative mean square error negative. So that's why we are having negative here. So we need positive values. So take the absolute and the mean of these 5 columns. So this is the mean and the absolute value. So now on the testing data set, so let's call it RG cross validation TS. Now we call it min of cross val score of RG, which is the model, X test, Y test, scoring equal negative mean squared error CV equal to 5. Cross val score is not defined. Okay, sorry for the typo. Cross val score, good. And here we need the absolute value of it. So print the absolute mean testing CV score is absolute np.min, so numpy.min of rg cvts 3 times, close the parentheses. So this is the score, the cross validation score of on the testing data set in its absolute value. So let's add more rows, cells. So let's plot the residuals and the prediction errors. For this you need to install yellow brick in Anaconda prompt or in the command prompt. So I did it in Anaconda prompt. So you go to the prompt, you type this code, conda install conda that forge two columns yellow brick yeah, or pip install yellow brick in the command prompt. Okay. So plotting the residuals. So here from yellowbrick.regressor you need yellowbrick.regressor. You need to import residuals plot. Residuals plot. Okay. Then you have your visualizer out here. Visualizer is residual plot of the residuals plot of the model Ridge Regression. And then you fit your visualizer, you fit it on X train and Y train. Then you need the score. Visualizer score. The score is on X test and Y test. And then we put it visualizer dot put. Let's run it. So this is the residual plot for the Ridge model with the training R square here, training S testing R square. So these are exactly what we got here. On the training 0.661, on the texting 0.663. Almost equal, they perform equally on training and the testing. It means that it's not good. Ridge regression does not really does not do a good job in predicting here. So here let's have the plotting, the prediction error from yellowbrick.regressor. We need prediction error. Then have our visualizer equal prediction error of the model Ridge Regression. This is the model talk about. Okay, add it here. That's here. Add it. Okay, about this add it. Same thing. Add it. So now we need to fit it. That fit on X train and Y train. We need its score. That score on X test and Y test. Let me change the syntax. Yep, still okay. Yeah, this is our prediction error. Best fit and identities. If you want it on the training, have the score on the training, we just change here. So this is the testing R square you have here. Testing R square. If you want to have your prediction error score on the training, you just change here. Train. And this the R square for the training, which is here. Train R square. So for comparison purposes, sometimes you need both of them, the scores on the training and testing, to see whether the model overfit or underfit when comparing the scores. Okay, so for research purposes you need both results on training and the testing datasets. So that's why people generally do that to compare. So let's now plotting the observed against the predicted. For this we need to import matplotlib.pyplot as plt. Let me see the spelling. matplotlib.pyplot as plt. Yes. Run it. So let's have for the training data set. Let's set the boundaries and the characteristic of the plot. AX equal PLT. We need the subplots, so subplots. Okay. We need the scatter plot of our observed and predicted data on a training data set. So X dot scatter by train, and it's predicted, its corresponding predicted value on the training data set. So X dot scatter by train and its prediction. Okay, let's finish. And we need the AX dot plot. We need to plot the boundaries, the min and the max here for the size to fit in. So plot parentheses brackets y min y train dot min y train dot max and again that's the lower boundary, the upper boundary. It's y train, same thing, dot min and y train dot max. Okay, so let's have the color as black, and the line style 2 dashes, and the line width, let's have it as 4. This is going to give us the line of best fit. Okay. Labeling. X dot set underscore X label X. We have observed private area, square kilometer, X dot set Y label you have predicted private area, square kilometer. Let's have the title, plt dot title, training observed versus predicted for the area. Then have plt dot show. Okay. Sorry, should be here instead of TS. So here we are on a training data set. So the prediction, here you have Y trend. So the corresponding predicted is RG pred tier. So sorry for the typo that caused this. So this is what we have on training data set, predicted against, observed against predicted XY. White pen, we are here. This causes the error. Yes, here. It's this. So we make the prediction on X train. So this is Y. So the corresponding, this is Y, the prediction, the corresponding of observed is Y observed. Here Y is predicted. Y observed, Y predicted. So let's come here. So this Y is the observed, and this is the predicted. So we want on the testing data set now for comparison purposes, as I said before, you just need to copy this and put here, and wherever there is training, you change the testing. So here you have test. Here instead of TR, it's TS now, and you change here test, 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 here training. Okay, that is going to give you the plot on the for the testing data set. Here testing, the type, testing, testing observer predicted for the theory. Okay. So now we are going to predict, plot the predicted and observed. Plotting the observed. Let's start with X. Observed and the predicted data on the same plot with lines. So let's do it on the testing only. If you want on the training, the procedure is the same. So we just, as we did here, we copy and we change wherever there is training, there is testing into, we change into trend. So you need to set the characteristic and the boundaries. So the plot, we need the plt dot rc params. That's to set the figure size. So figure dot fix size equal to 10 and the 6, say 10 and the 6. The size of the figure 10 and the 6 ax equal, let's have out the range. It's going to range of x first. You want it on the x-axis, so and now we plot plt dot plot. We plot our ax here, the range of x, and we plot the y-test, this is the observe data on the testing data set, and we label it as observed. And we give it a color, which is, we take it dark color, and then the line style equal, I take a dash, and the line width, I put it 1.5. So this is for, okay, let's continue. It's not finished yet. plt.plot now. X, ax, 0, x, 8x. Now we are going to plot the predicted value. So the RG, red TS, and the label is predicted. Let's put capital here. Let's give it color. Color equal blue. Line style. Let me see here. Line style. Take blue dashes. And the line width equal 1.3. Here, edit it. Okay, good. Okay, so this is what you have. The observed value is on X, on the taxing data set are in blue, in black. The predictors are in blue. So both of them on the same plot instead of against each other. You see here for a better comparison. Okay, so let's have the labels. So plt dot x label, we call it sample. The data sample on the testing data set, or testing data set sample, and then plt dot y label, let's call it credit area, in square kilometer. Credit area here from the sample. Let's have a legend, plt dot legend. We have boundary box 2 anchor. Let's have for x 0.5 and for y negative 0.2, for instance, because we see here the predictors, they go down a little bit down, so it may on y it may go maybe below 0. Okay, so location, we need it to be lower center, so below the plot, and the number of columns you have predicted and observed and predicted, so 2 columns. And do we need the frame or not? Frame on. Sorry, have notification here. So frame on, I say no. So false. Okay. And a plt dot show. So this is what you have here, the legend, observed, in black and predicted in blue. There is no frame on it, around it. So this is on testing data set. If you want on the training, just change this to 3. In this codes, this line of codes, you change here, X train, here Y train, and the RD pred TS is going to be RD pred TR. So let's have it, just copy. sorry, with my cursor, train, right train, and the prediction. So this is the range for length of X train. This is plotting the Y train, and this is plotting the predicted of Y train. That is all. And then you run, and this is what you get on the training data set. Comparison purposes. So you see here is the density of the prediction. The predicted data here is not as what you get here from the training data set. See the density here? It's really, it's very dense here. Only the size of the data. Yeah. Okay, so this is the end of the video. I hope it will help some people who are doing research. So I said, as I said before, for research purposes, you need to go to 10 as cross validation. I put 5, but 10 is better. So GridSearch function used with Ridge Regression to train the hyperparameters, get the best parameters, then you continue fitting your model on the training, and then having the model performances on the training and testing data set, and you continue with your plots, cross validation on the plots. So thank you very much for watching. Hope to see you soon.